So the next point is imperfection in the solids. Already we know that crystalline solids they are having regular arrangement of constituent particles for the long range. Even though they are having a regular arrangement of the constituent particles, these crystalline solids are not yet perfect, because those crystalline solids, they are made up of large number of small crystals, and these small crystals, they are having a defect in them. That defect in the solids is nothing but it is the irregularity in the ideal arrangement of the constituent particles. That is called as defect in the crystals. And this happens when the crystallization takes place at very fast rate or at the moderate rate. A perfect crystal is formed whenever the crystallization takes place at a slow rate here. Here in the imperfection of the solids, there are two types. One is a line defect and another is what? Point defect. Line defect is nothing but it is the irregularity in the arrangement of entire row of the constituent particle. For example, if I take the arrangement of these constituent particles which repeats periodically like this, okay, here complete one row of particles will be missing here. This is called as irregularity in the arrangement of entire row of the particle. That particles are missing here. That is called as what? Line defect. One line is missing means that is line defect. Here in case of point defect, it is the irregularity in the ideal arrangement of particles around the point here. So one point is missing here. Here one point is missing means that is a point defect. Okay, one lattice point is missing. So these are the line defect in which complete line of the constituent particle is missing. So these defects, they will produce what? That defects in the solids. There are again point defects for our syllabus. There are three types, that is stoichiometric defects, non-stoichiometric defects and impurity defects here. Again in the stoichiometric defects, there are two types, vacancy defect and interstitial defect, and in case of non-ionic solids they are called as vacancy and interstitial defects. The same defect in case of ionic solids, vacancy defect is called as SCHOTTKY defect and interstitial defect is called as what? FRENKEL defect here. Next, non-stoichiometric defects. In this one again there are two types, metal excess defect is there and metal deficiency defect is there. In the metal excess defect again there are two types, due to the anionic vacancy and due to extra cation. Now we will study one by one in detail. Now we will discuss stoichiometric defects. These stoichiometric defects will not affect the stoichiometry of the compound, and there are two types, vacancy defect, interstitial defects. In case of vacancy defects, whenever some lattice points are missing from the crystal, then the crystal is said to have vacancy defect. In this crystal, two lattice points or two constituent particles are missing here, and then it is called as what? Vacancy defect. Since particles are missing, mass of the crystal decreases, hence density also decreases. In case of vacancy defect, density of the crystal decreases, and this vacancy defect, it is produced just by heating the crystal, so that some of the lattice points will be missing. This is in case of non-ionic solids. The same vacancy defect in the ionic solids, it is called as SCHOTTKY defect. In the SCHOTTKY defect, this is in case of ionic solids. Already we know that in ionic solids, cations and anions are arranged in the three-dimensional network, so that an ionic solid is electrically neutral. Number of cations will be equal to number of anions here. And in case of SCHOTTKY defect, in order to maintain the electrical neutrality, suppose one anion is missing from the crystal, along with this one cation will be missing, so that electrical neutrality is maintained here. In case of SCHOTTKY defect, equal number of cations and anions will be missing in order to maintain the electrical neutrality. That's why the number of cations missing will be equal to what? Number of anions missing here. And this type of SCHOTTKY defect, it is observed in the ionic solids which are having almost the same size of cation and anion here. In this case also, again the density of the crystal decreases, because particles are missing, mass decreases, again density also decreases. Example for this one is NaCl, KCl, cesium chloride, and here AgBr is very important example, because it shows the SCHOTTKY defect as well as FRENKEL defect here. Now there are 10 power 6 SCHOTTKY pairs are present in 1 cubic centimeter, and in 1 cubic centimeter 10 power 22 ions are present here. So that 10 power 6 SCHOTTKY pairs are present in 10 power 22 ions. So one SCHOTTKY pair is present in x number of ions. X is equal to what? 10 power 16. So one SCHOTTKY pair is present in 10 power 16 ions here. Next one, interstitial defect. In the interstitial defect, whenever an constituent particle occupies interstitial site, whenever an extra constituent particle occupies interstitial site like this, then it is called as what? Interstitial defect here. So because of interstitial defect, density of the crystal increases because here extra constituent particle is occupying interstitial site here. And the same interstitial defect in case of ionic solids, it is called as what? Frenkel defect here. In case of Frenkel defect, one of the cation from its original site, it will be dislocated and it will occupy some other interstitial site here, so that it creates a vacancy defect at its original site and an interstitial defect at its new location. Suppose if I take this cation is dislocated from its original site and it will occupy an interstitial site like this. In its original position, it will create a vacancy defect, and at its new location it creates what? An interstitial defect here, and hence it is also called as what? Dislocation defect, where a smaller cation is dislocated from its original site to an interstitial site here. So this is also called as dislocation defect. There is no change in the density of the crystal because just one cation is dislocated from its original site to an interstitial site here. So there is no extra particle is coming and no particle is missing from the crystal here. So this is called as what? Frenkel defect. In this one, this type of Frenkel defect is observed in case of ionic solids which are having small size cation and large size anion. Example is zinc sulfide, AgCl and AgI. Very important example is AgBr. This AgBr shows Schottky defect as well as Frenkel defect here. This is what vacancy defect, interstitial defect, Schottky defect and Frenkel defect. Next one. So the next type of the defect is non-stoichiometric defects. In this type of defects, the cations and anions are not present according to the stoichiometric ratio here. So that cations and anions, they are not present in the equal number as they are represented in the stoichiometric formula. Some of the cations may be extra or some of the anions may be missing here. So always you keep in mind, defect is nothing but the constituent particles are missing or some extra constituent particle, they will occupy the interstitial site. In case of the ionic solids, what happens here? Cations may be missing or some of the extra cation may be coming and they will be occupying some interstitial site here. So in this case, non-stoichiometric defects, there are two types. One is metal excess defect and another is metal deficiency defect. So the name indicates metal excess defect means always the metals, they will form cation, so that they will be having excess of cation. That excess of cation is due to the presence of more number of cations or some of the anions may be missing. If the anions are missing means automatically the number of cations will increase here. Another thing is metal deficiency. As the name indicates that metals, they will form what? Cations. Here these crystals, they will be having less number of cations as compared to the stoichiometric ratio here. Now in case of metal excess defect, there are two types, that is due to the anionic vacancy. So that anions are missing means automatically the number of cations will increase. Due to extra cation that is occupying the interstitial site here. So for this one, the example is NaCl. So I will take here NaCl crystal, and in case of NaCl crystal, already we know that Na plus ion and Cl minus ion, they are arranged in the three-dimensional network. So that these are ionic solid in which cations and anions are arranged here. Whenever this NaCl crystal, it is heated in an atmosphere of sodium vapors, what happens? Some of the sodium atoms, they will deposit on the surface of this NaCl crystal. Then one of the Cl minus ion from the NaCl crystal, it will come out of the crystal, then it will combine with this sodium atom to form NaCl, during which this sodium, it releases an electron. Then this electron, it will occupy the anionic vacancy that is created by the Cl minus ion. That electron will come here and it will occupy this anionic site here. So that in order to maintain the electrical neutrality, already one anion is missing means that negative charge is missing, so that is compensated by the electron here. So this anionic vacancy that is occupied by the unpaired electron, this one, this is called as what? F center we call it as. This is very, very important, you have to remember. In which defect F centers are observed, this is called as F center. This is nothing but the anionic vacancy that is occupied by an unpaired electron, that is called as what? F center. These F centers, they will impart color to the crystals. For example, in this one, what happens? this unpaired electron, it will impart yellow color to the NaCl. That color is due to the excitation of electron by absorbing the energy from the visible region, obviously. So what happens here? One of the Cl minus ion will come out of the crystal that combines with sodium to form NaCl, during which this sodium releases an electron. So whenever Cl minus ion is coming outside, one anionic vacancy is created. So to maintain that electrical neutrality, that anionic vacancy is that is occupied by the electron which is lost by the sodium here. So that is called as what? F center, which imparts color to the crystal. Similarly, excess of lithium, sodium and potassium. Suppose excess of lithium is there, it will impart pink color to the crystal. If excess of sodium is there, already we know this one, it will impart yellow color to the crystal. If excess of potassium is there, it will impart violet color to the crystal. This is about that is metal excess defect due to the anionic vacancies. That is, F centers are observed in the metal excess defect due to the anionic vacancy here. Next one, due to extra cation. This type of defect is produced whenever an extra cation that occupies interstitial site here. So these crystals, they are having excess of cations. That is, whenever zinc oxide, for this one example is zinc oxide. So whenever zinc oxide is heated, it is white in color. On heating, it loses oxygen and it will turn into what? Yellow color here. So for pure zinc oxide, the formula is ZnO it is. So whenever the defect is created, then it is having excess of cations, then its formula become as what? Zn, that is 1 plus X, then oxygen you will get. So that the crystal is having excess of cation. Now these excess of cation, they will occupy the interstitial site. So in order to maintain the electrical neutrality, along with this Zn plus 2 ion, these two electrons, they will occupy the neighboring interstitial site, so that electrical neutrality is maintained here. So this is example for what? Extra cation, that is metal excess defect. In case of metal deficiency defect, as the name indicates, already we know that it contains less number of cations as compared to the stoichiometric ratio. So if I take the example of FeO, in case of pure FeO, Fe and oxygen, they are present in 1:1 ratio. This is pure, 100% of Fe plus 2 ions are present and 100% of oxide ions are present here. But most of the time this FeO it is found in the form of Fe, that is 0.95:1 here. So this is having some defect. In this one, what happens? Fe plus 2 ions are present only to the extent of 95% and oxide ions are again 100%. So that some of the metal is missing here because cations are missing. So in the FeO crystal, Fe plus 2 ion and O minus 2 ions are there. And in this one, what happens? Some of the Fe plus 2 ions are missing. In the FeO crystal, Fe plus 2 ions are missing here. So one Fe plus 2 ion is missing here. What happens? One Fe plus 2 ion is missing means two positive charges are missing. So in order to maintain the electrical neutrality, that is the remaining two Fe plus 2 ions, they are converted into what? Fe plus 3 ion. So here it will be converted into Fe plus 3 and this will be converted into what? Fe plus 3. So what happened here? The loss of the positive charge is balanced by the required number of Fe plus 3 ion. To balance the positive charge, this Fe and Fe, they will convert into what? Plus 3 oxidation state. Then the number of positive charges and the negative charges will be equal here. This is about metal deficiency defect here. Next one. So the next type of the defect is impurity defect here. Okay. In this one, what happens? This defect is created due to presence of impurity atom in the crystal. For example, if I take NaCl crystal, in this one some impurity atom is introduced, means then some defects are produced in the NaCl crystal. We know that this NaCl crystal is electrically neutral, so that number of cations will be equal to number of anions, because ionic solids are always electrically neutral. For example, here NaCl crystal containing small amount of strontium chloride as the impurity. In this case, what happens? Each strontium plus 2 ion, it displaces 2 Na plus ion, because in order to maintain electrical neutrality, 2 positive charges are coming inside, means 2 positive charges must go outside here. That's why here each strontium plus 2 ion, it displaces 2 Na plus ion, so that 2 Na plus ions are displaced here. So that 2 cationic vacancies are created. Here 2 cationic vacancies are created. This strontium plus 2 ion, it occupies lattice site of 1 Na plus ion, so that here one strontium plus 2 ion is occupied here, and the other lattice site of the Na plus ion is left vacant. So that in this way some defect is created in the crystal here. Each strontium plus 2 ion displaces 2 Na plus ion. Out of that, it occupies lattice site of one Na plus ion and other will be left vacant here. So that the number of strontium plus 2 ion present in the crystal will be equal to the number of cationic vacancies produced here. Yes or no? So here we can write the number of strontium plus 2 ions will be equal to the number of cationic vacancies produced. So this is what the impurity defect here. Another example is AgCl, that is containing cadmium chloride as the impurity. In this one, cadmium plus 2 ion, it displaces 2 Ag plus ion. Like that it will continue. The next one. So the next property is electrical property. Based on the electrical property, solids are classified into 3 types, that is conductors, semiconductors and insulators. In case of conductors, their conductivity ranges from 10 power 4 to the 10 power 7 per ohm per meter. Semiconductor 10 power minus 6 to the 10 power plus 4 per ohm per meter. In case of semi-insulators, that is 10 power minus 20 to the 10 power minus 10 per ohm per meter. So here the conductivity of semiconductors that lies between the conductors and insulators here. Another theory that explains the conductivity of these solids, that is a band theory we call it as. One thing you keep in mind, for a good electrical conductor, the valence bond, that valence band must be partially filled. Or if the valence band is completely filled, it must overlap with the conduction band. Okay, this is the condition for very good electrical conductor, and this happens in case of the metal. The valence band is partially filled or this valence band is overlapped with the conduction band, hence the metals will show maximum conductivity. Therefore electrons can easily flow under the influence of applied electrical field here. So example for this conductors is what? Metals. In case of metals, valence band is partially filled, or if it is completely filled, it is overlapped with the conduction band. In case of semiconductors, the gap between the valence band and the conduction band is very small, so that whenever electrical field is applied, some of the electrons can easily jump into the conduction band and they will show a small amount of electrical conductivity here. And the conductivity of these semiconductors can be increased with increase in the temperature. If the temperature is increased, more number of electrons can jump into the conduction band under the influence of electrical field, so that their conductivity increases here. Then what happens? And such type of semiconductors are called as what? Intrinsic semiconductors. Example for that is silicon or germanium. So these are the pure semiconductors, that is silicon you can take, or you can take germanium here. So they are having very small conductivity, but the conductivity of these intrinsic semiconductor, it is very less, so that it is not useful for the practical purpose. So in order to increase their electrical conductivity, these intrinsic semiconductors, they are added with some amount of impurity atom. So those impurity atoms, they will create some electronic defects in the intrinsic semiconductor, so that will be responsible for increase in the electrical conductivity of the intrinsic semiconductors. So the process of adding impurity atom to the intrinsic semiconductor, that is called as what? Doping, that is addition of impurity atom. The added impurity atom is called as what? Dopant. And here this dopant, it may be electron rich or electron deficient with respect to the silicon or germanium. Such doped semiconductors, they are called as what? Extrinsic semiconductors, whose conductivity will be more than that of the intrinsic semiconductors here. We will discuss this extrinsic semiconductors in detail. Next is insulators. In case of insulators, the energy gap between the valence band and the conduction band is very high, so that electrons cannot jump into the conduction band, hence they will not show any electrical conductivity. For example, glass, plastic and rubber here. And our next concentration is, that is extrinsic semiconductor, and these are further classified into 2 types, that is N type and P type. We will discuss now. So the next concept is extrinsic semiconductor. There are 2 types of extrinsic semiconductor. One is N type of semiconductor and another is P type of semiconductor. Here N type of semiconductors are obtained by adding pentavalent impurity to the group 4A elements, that is to the silicon or germanium. For example, if I take silicon, it is a group 4A element which is having 4 valence electron. Whenever it is doped with pentavalent impurity like phosphorus, which is having 5 valence electron. And whenever this phosphorus is added to the silicon, some of the lattice sites of silicon, they are occupied by what? Phosphorus atom here. This phosphorus is having 5 valence electron and silicon is having 4 valence electron. Group 4A and 5A elements here. Out of 5 electrons, 4 electrons are utilized to form a bond with the silicon, and 5th electron is free here. This electron is free means it is free to move and it is delocalized, this electron is responsible for increase in the electrical conductivity of these extrinsic semiconductors. Since increase in the electrical conductivity is due to the negative charges here, it is called as N type of semiconductor. In case of P type of semiconductor, they are obtained by doping silicon or germanium with a trivalent impurity like boron or aluminium. For example, if I take here germanium, which is having 4 valence electrons. Whenever it is doped with a trivalent impurity like boron or aluminium, which are having 3 valence electron. Whenever boron is added to the germanium, some of the lattice sites of germanium are occupied by what? Boron. And this boron is having only 3 electrons. All the 3 electrons are utilized for the bond formation and then it is having one vacant orbital. And due to presence of this vacant orbital, that is called as what? It is a electron hole, we call it as, or it is electron vacancy. Due to the presence of electron hole, their electrical conductivity increases and these are also called as positive holes here. Hence, the increase in the conductivity is due to the positive hole. They are called as what? P type of semiconductors. This is what N and P type of the semiconductor. Then the some of the application of N and P type of semiconductors, that is some electronic components are there. That is diode is one of the electronic component which is the combination of P and N type of semiconductor and it is used as rectifier. The most important example for the diode is that is a solar cell, which is a photodiode which converts sunlight into electrical energy. Next, triodes. These triodes are nothing but sandwich of PNP type of transistor or it is a NPN type of the transistor and which are used to amplify the audio signals. And some of the semiconducting materials are prepared by the combination of group 13 and 15 elements and by the combination of group 12 and group 16 element. That combination is aluminum, phosphorus, gallium, arsenic and indium and antimony. These are very fast responding semiconductors. And again here just zinc and sulfur, cadmium, selenium, mercury and tellurium. So all these are mixed together just in order to get an average valency of 4 so that they will act as semiconductors. And some of the transition metal oxide like TiO2, CrO2, that is ReO3, all these are showing some metallic behavior. This ReO3 is similar to that of copper in its conductance as well as in the appearance. And these VO, VO2, VO3 and TiO3, these are also showing some metal as well as insulating character based on the temperature variation. So the next concept is magnetic property. Each substance is associated with a definite amount of magnetic property. That magnetic property of the substance is due to the presence of unpaired electrons in the substance. These unpaired electrons, they will act as small magnets. And here the magnetic moment due to the spin motion of the electron, that is calculated as mu is equal to square root of n into n plus 2, that is Bohr's magneton. This is spin magnetic moment formula here. N is equal to what? Number of unpaired electrons. And here 1 Bohr magneton is equal to 9.27 into 10 power minus 24 ampere meter square it is. Okay. Now this magnetic moment of the electron, that magnetic property for the electron, it arises due to the two types of the motion, that is orbital motion of the electron and another is spin motion of the electron. This is the nucleus and around this nucleus electron is revolving, that is called as orbital motion. In addition to this, electron is spinning about its own axis, that is called as what? Spin motion of the electron. Because of these two motion, electron is associated with some amount of magnetic property. Because electron being a charged particle, it is undergoing all these motion, it is considered as what? Loop of the current, and that loop of the current is associated with some amount of magnetic property here. Now based on the magnetic property, these solids, they are classified into paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic substances. These paramagnetic substances are nothing but these are weakly attracted by the external magnetic field. Whenever external magnetic field is applied, these paramagnetic substances, they are weakly attracted by the applied magnetic field because they are magnetized in the direction of the applied magnetic field here. And this paramagnetism is due to the presence of unpaired electrons in the substance. So examples are what? The species which are having unpaired electron, copper plus 2 O2 is paramagnetic and Fe plus 2 and Cr plus 3. Any species which are having unpaired electron, they are what? Paramagnetic in the nature. And these paramagnetic substances, they will lose their magnetic property in the absence of the magnetic field. Next is diamagnetic substances, and these are having only paired electrons. So these are having paired electron, means pairing of the electron cancels the magnetic moment of each other. Hence these diamagnetic substances, they are weakly repelled by the applied magnetic field and they are magnetized in the direction opposite to that of applied magnetic field here. And the example is HCl, H2O and benzene. Next one is ferromagnetic substance. This is very, very important. This is the extreme situation of the paramagnetism, which are having more number of unpaired electrons here. And these ferromagnetic substances, they are strongly attracted by the applied magnetic field and they will retain their magnetic property even after the removal of the applied magnetic field here, so that they are magnetized in the direction of the applied magnetic field. And in case of ferromagnetic substances, all the domains are arranged in the direction of applied magnetic field here, all are in the same direction. So the example for this ferromagnetic substance is iron, cobalt, nickel, gadolinium and chromium oxide it is. Next is antiferromagnetic substance. So these two are almost same, but here the domains are oppositely oriented. Here antiferromagnetic substances, they are having zero magnetic moment because in the antiferromagnetic substances domains are oppositely oriented and magnetic moment cancels with each other here. That's why what happens here, magnetic moment is zero. See here the domains, they are oriented in the opposite direction, so that the magnetic moment of one domain will get cancelled with the another. That's why they are what, having zero magnetic moment. Example is MnO, MnO2, that is manganese oxide, so you can write here. Now the last one is ferrimagnetic substance. In this one, the domains are arranged in the parallel and anti-parallel manner in the unequal number. That is, in the unequal number, they are arranged in the parallel and anti-parallel manner, so that they are weakly attracted by the applied magnetic field here. So these are ferrimagnetic substances. Examples are these iron oxide, magnesium iron oxide, zinc along with iron oxide. These are the examples here. The next important point is the temperature at which ferromagnetic substance will be converted into paramagnetic substances. The temperature is called as Curie point. You have to remember here. The Curie point is nothing but these ferromagnetic substances, on heating they will convert into paramagnetic substances. So the temperature at which ferro become para, that is called as what, Curie point here. Okay, this completes magnetic property of the solids.